Now let's talk about simple linear regression. I will, as usual, introduce it in general form first, give you some examples, and then we will discuss all details of the method. Okay. Well, the simple regression is the simplest regression you can make, actually. When you have just one y and one x variable. For example, you want to predict weight by measuring height, or you want to predict income of person by knowing his or her age. Okay. And then you have a function that brings these two variables together. If this function is linear, then it's a linear regression. If this function is nonlinear, it means that it's nonlinear regression. Okay. Here are some examples. Linear regression looks like this. So you have, this is your y variable, this is your x variable, and then we have two parameters, beta0 and beta1. We will discuss these parameters later. Then you always have this epsilon. What is epsilon? Epsilon, it's an error. Which means the following: when you have x and y, the real data sets, it's very rarely, almost never, where all points lie on a straight line. You will always have some scattering around this straight line, and the scattering is explained by epsilon. So epsilon is just the difference between a point on a straight line and the real position of the point. Okay, and then we use beta and epsilon. We use Greek letters because in this particular case, I'm talking about the population. How we can make a nonlinear regression? Well, we already know that you can make an exponential regression, for example, right? But very often you make it as a polynomial. So in this case, I use a polynomial of degree 2. It's not full polynomial. It's just the quadratic term and the coefficient b0, right? So in this case, you will get a parabola, which is, of course, a nonlinear. It doesn't look like a line, right? In this course, we will talk only about linear regression, but most of the things we are going to discuss, they will work equally for nonlinear regression as well. So the main goal, the process of calibration, is to find the coefficients, beta0, beta1, beta2, and so on, that fits your data points well. But what it means, fits data points well, that's what we are going to discuss. Okay. First of all, let me show you just a simple difference between linear and nonlinear. The regression, it's quite simple. Linear regression means a points line on a straight line, so the model is a straight line. And then if it's regression is nonlinear, so it's a curve. Okay, so in this case, you can see that we have two sets of points. In the left part, indeed, line is a very good approximate of the trend of these points, or the behavior of these points. But on the right part, you can see that we cannot make a good model with just a straight line. So we need a nonlinear function. This case. Sample and population, we are going to use beta as a coefficients for population, and we will use b as a coefficients for a sample. And the same about the random error. So we have epsilon here and we have e here. So that's what we are going to use as a representation of linear regression model for a sample. Now let's quickly talk about the meaning of these two coefficients, b0 and b1. Well, let's say this is our sample and this is our model. Okay, so this is the line that fits the data best. The b0 is called intercept or y-intercept. So it's a very simple thing. Look, if x is equal to 0, so if you don't have any x value, then y will be equal to b0, right? Note that I use another letter here. It's yp. It means predicted y. So it's a point that is lying on a straight line. Okay, and because it's a predicted value, I don't have any errors. I don't have this error term e here. Okay, so b0 is an intercept. It's what y is equal to when x is equal to 0. And then b1 is a slope. So if you make a triangle like this, then the ratio between d and c, in this case we have two cathetas, d and c, is a slope. So for example, if b1 is equal to 1, it means that the line is 45 degrees oriented, right? You can think about slope is the following. Slope tells you what happened to y if you increase x by 1, okay? For example, if we are talking about height and weight, how big the weight will be if you height, for example, you have 170 and 171 centimeters. So if we take the difference between weight of these two persons, what will be the difference? Okay. So as a summary, you have a dependent variable, it's y, you have independent variable, it's x, then you have y-intercept, it's b0, you have a slope, it's b1, and then finally you have a random term. And as often in statistics, your data should meet some requirements in order to use the linear regression model. And the requirements are following. First of all, the relationship between x and y should be linear or close to linear, right? So otherwise the regression model will not be a good mathematical model describing the relationship. The second, we assume that x values are measured very precisely, so we almost don't have any errors in the x measurements. And the y errors, so how we measure y values, we assume that we have errors, but these errors are random values and distributed normally. Okay, most of the time it will be like this. Most of the time the measurement errors are normally distributed, and we already know how to assess them. If you know the error values, you can always use a cuckoo plot or normality test like we did it with ANOVA in order to see if they are indeed normally distributed. Okay. And then the idea is that for every x value, the variance of the variability of y values should be almost the same. So if your data meets these requirements, then you can use a regression model for describing the relationship between x and y and for predicting y by knowing x. Now let's talk about the relationship between correlation and linear regression model. As we know, both actually assess a linearity between two variables x and y. But what's the difference? Well, you remember, correlation tells you how strong the relationship is. So it means that how strong the values, the points to a straight line, okay? But you cannot use correlation for predictions. It just tells you how close the points to the straight line, but it does not give you any ideas about the orientation of this line. Linear regression estimates the magnitude of relationship. It doesn't tell you how strong the relationship is, but it tells you what happened to y if we change x to the particular value, okay? And just a couple of examples. If we are talking about prediction of house price by only age of the house. In this case, the regression will tell you what happened to the price in average if the house will be 10 years older. Okay. Or for example, if we are talking about, let's say we would like to make a popcorn and we use different time for that. And every time we make a new popcorn, we measure the quality of this popcorn just by assessing the quality ourselves or our friends with our friends. So if you make a regression model that tells you the dependence between the quality of popcorn and time you use to make a popcorn, then you can predict, for example, what if we use 40 seconds instead of 60, how it will influence the quality of the popcorn. If, of course, the quality of popcorn and the time for cooking have linear relationship. Let me clarify this maybe a little bit misleading issue with y and yp. Why sometimes I use y and why sometimes I use yp. The idea is following. When you use y, it means that the real measured value, and it always contains errors. It always contains errors because it's not possible for the points, for the experimental points to lie exactly on a straight line. When we use yp, we assume that yp is a predicted value, so it means it lies on the straight line. It means that we can use this to define error of prediction. What it means? The error of prediction is simply a difference between the real y value and the predicted y value, what model gives us. Okay. So every time when we have an error term, we will use y here. But if we don't have error term here, so nothing here, then we will use yp. So assuming that in this case the y, the points is lying exactly on a straight line, it's what model predicts. And then let me show you an example. In this case, I made a model, a linear model, that brings together age in years, which is x, and income in amount of euro per year, which is y in this case. You remember that's the people data. So we have 32 points, and this is the red line. It's a model. It's a linear model. So you can think of first of all, the parameters of this model. They look like this, and they tell measure x or take ask for age. Then multiply age to 130, and then subtract 1156, and then you will get a salary or income. Okay, so that's your model. It looks like a straight line, and you have intercept and you have the slope. Okay. Now let's take a particular age. For example, we have 33. Okay, so this is the true value y, and this is the predicted value yp. So you can see that yp and y are not the same. You always have something in between. And this something in between is exactly e. It's an error of prediction. So we either write our model like this, like I have done already, yp equal to, in this case, 830 times x minus 1156, or we write it like y equal to 830 x minus 1156 plus e, where e it's exactly a difference between the real y value and the predicted y value.